Welcome to the deep dive. Today we're looking at a single master plan. It's aiming to totally change how we think about rain.
That's right. Not just a problem to get rid of, but maybe a resource we can actually use.
Exactly. It's this idea of combining serious flood control with, well, advanced water reclamation.
And the main goals, what we want you to take away, really boil down to three key
Okay,
things.
okay.
First, tackle urban flooding,
Yeah.
reduce that risk. Second, capture that stormwater runoff, conserve water.
Right.
And third, transform that water from a liability into something valuable and reusable. Safely, of course.
So let's follow the water from, say, the street all the way through to being purified.
Sounds good.
Now, the plan obviously built on phase one groundwork, the hydrological surveys, figuring out where water goes. That included the environmental impact assessments, too.
Oh, absolutely. Essential groundwork. That dictates how you design the physical system. So now we get to the actual construction, the collection part. And the thinking shifts here. It's about capturing a resource. So you have your storm drains, your big culverts.
The usual suspects.
Right. But they lead quickly to initial debris screening. We're talking trash racks, bar screens, designed to yank out the big stuff, branches, plastic, whatever.
To stop blockages later on.
Exactly. Prevents major headaches downstream.
In this whole collection phase, what's the linchpin, the most critical bit?
I'd have to say the sedimentation ponds and reservoirs, they're doing double duty, which is clever.
How so?
Well, first, yes, flood attenuation. They hold back those big surges of water temporarily,
Yeah.
manage the peak flow.
Right, buffering.
But that holding time, it also allows for primary settling. Heavy stuff, sand, silt, grit just drops out naturally using gravity.
Ah, so it's like a free first stage of cleaning, saves energy later.
Precisely. Cuts down the load on the more intensive purification steps coming up.
Okay, so the big stuff and the heavy grit are mostly out. Now we move into the proper treatment stages. Tiered treatment, I think it was called.
That's the concept. Moving from physical removal, then biological, then high-tech polishing. So after the ponds, you hit primary treatment.
What does that involve? More screening.
Yeah, some finer screening, but the key component here is the grit chamber.
Grit chamber, okay.
Its specific job is to slow the water flow right down. Just enough so smaller, dense things like sand and gravel settle out.
Seems basic. Is skipping that really a big risk? Dedicating a whole structure?
Oh, definitely. Think of that grit as, well, liquid sandpaper.
Mm-hmm.
If it gets further into the system.
No damages things.
Exactly. Wears down pumps, pipe work, and especially the more delicate equipment in the later stages. It's crucial preventative maintenance, really.
Makes sense. Protect the investment. Okay, after grit removal, we get into secondary treatment. This is where nature comes in. Constructed wetlands.
Correct. This is the low-energy biological powerhouse. You create these wetland environments with specific plants, microorganisms.
And they just eat the pollutants.
Essentially, yes. They consume the dissolved organic matter. The wetlands do a lot of the heavy lifting biologically, and the plan also mentions biofilters.
That's another layer.
Sort of a focused version. Media packed with beneficial bacteria to target pollutants that the wetlands might have missed.
Okay, so nature's done its bit. Then we jump to the really fine cleaning, tertiary treatment.
Now we're talking high-tech. This stage uses membrane filtration. Think microfiltration or ultrafiltration.
Like superfine physical barriers.
Exactly. Microscopic pores that physically block suspended solids, bacteria, even viruses. A very effective physical sieve.
And reverse osmosis is mentioned too. Is that always needed?
It's often an optional step. If you need extremely high purity water, maybe removing dissolved salts or minerals, then RO comes in. But for many non-potable uses, standard membrane filtration is enough.
Got it. And the final step before it goes anywhere is disinfection, making absolutely sure it's safe.
Critical step. The plan looks at a couple of main options. Chemical-free, like UV light.
How does UV work?
It uses ultraviolet light to damage the DNA of any remaining pathogens, like bacteria or viruses, so they can't reproduce. Sterilizes the water.
And the alternative.
Chemicals.
Right. Traditional methods like chlorination or maybe ozonation.
Why offer both UV and chemicals?
Trade-offs. UV is great, no chemical residuals, very effective. But sometimes a chemical disinfectant like chlorine provides a residual protection that lasts a bit longer in the pipes. It depends on the specific end use and local regulations, costs too.
Okay, so the water is treated, it's disinfected. Phase 4 is about getting it where it needs to go.
That's distribution. The treated water goes into storage reservoirs and then out through a completely dedicated pipeline network.
Dedicated. meaning separate pipes from drinking water.
Absolutely crucial. This reclaimed water is only for non-potable uses. Things like landscape irrigation, industrial processes like cooling, maybe toilet flushing in new buildings.
So it frees up the high-quality drinking water for, well, drinking.
That's the core benefit for water conservation. But this whole system, its success, really depends on people trusting the water quality, doesn't it? Which brings us to phase 5, monitoring.
Continuous water quality monitoring. This is non-negotiable. It's the safety net.
How continuous is continuous?
We're talking sensors placed at key points throughout the entire treatment train and in the distribution network. They check parameters like pH, turbidity, disinfectant levels, even pathogen indicators in near real time.
So not just spot checks, it's constant oversight.
Minute by minute, essentially. Automated alerts if anything drifts outside safe limits. It ensures standards are met before the water is delivered. That's vital for public confidence and safety. Plus, there's planning for future upgrades built in.
Stepping back then, the big picture here is quite profound.
It really is. It shows how smart infrastructure can turn something we dread, flooding, into a reliable, sustainable asset. It fundamentally improves water security.
Which leaves us with a thought for you, the listener. This plan cleverly blends natural systems, those constructed wetlands, doing biological work with very high-tech engineering, like membrane filters and UV. Given what we know about climate change, more extreme weather, which part of the system do you think will prove more resilient in the long run? The natural component or the engineered one? Something to ponder next time it rains.